Hi everyone. Our topic of the presentation is a comparison study between the NoSQL and PostgreSQL on text searching. Our group members include Kecheng Xiao, Tongchen Yi, and Xuanzhi Huang.
Here is the background of SQL and NoSQL. Early in the 1970s, SQL and RDBMS emerged, and since then, they have ruled the database software industry with their clean and easy to understand language structure, and the asset, or called the atomicity, consistency, isolation, and durability. These four properties have ensured the overall stability of the system. As its definition, RDBMS are built with relational models which organize data into tables or correlations with unique keys. The logical connection or correlationship is another main feature which allows the users to provide the basis of interaction among tables. However, with the fast development of the webs, the requirement of handling large volumes of data with multiple formats exposes several constraints of the traditional SQL, or called SQL. As a result, NoSQL, or called the not only SQL, emerged. It emerged in early 2000s, and it provides a mechanism for storage and retrieval of data that is modeled in means other than the tabular relations used in the relational databases. Besides, it has simpler horizontal scaling to clusters of machines, and is particularly useful for storing unstructured data, such as chats, emails, and images. And this kind of data, they grows far more rapidly than the structured data, but they do not fit the relational schemas of RDBMS. There are four main types of NoSQL databases, including the document databases, key value databases, one column databases, and graph databases. The most famous database for the text data is called MongoDB, and this is what we introduce and study today.
Our motivation of doing this project starts with the high demand of text search. As we all know, almost all search engines have some kind of text search and content matching methods. So by understanding how text search is implemented in NoSQL and SQL is very beneficial. And nowadays, almost all database management systems abandon traditional SQL and go with the NoSQL. We want to see whether this is a wise choice or not. To be more specific, we want to compare the native support of NoSQL and the extensive support of SQL in text search.
Next, I'm gonna talk about the data. The data we used in our study is from Hamlet, which is a very famous tragedy written by William Shakespeare. We select 6 scenes from the whole play, that is scene 1 to 4 in Act 1 and scene 1 and 2 in Act 2. Therefore, we separate the corpus to 6 text sections, and each section has 4 attributes: ID, title, description, and text respectively, where the ID is the index of corresponding text section, and the title is the heading of corresponding text section. The description is some setting of the play, and finally the text is the main body of the play script. The techniques and tools we used are very straightforward, since we want to compare the performance of NoSQL and traditional relational databases on text searching. We select one database system from each category and do some experiments about searching with the Hamlet script on them for performance comparison. We choose MongoDB as the representative for NoSQL and PostgreSQL as the representative for relational database management system. MongoDB is the most popular NoSQL database management system. Instead of storing the data into columns and rows of relational databases, the data objects are stored as documents in JSON format. Each document contains pairs of fields and values and has a unique key, object ID, that is used for identification. The values can usually be of multiple types, including strings, numbers, booleans, arrays, and objects. In addition, MongoDB supports horizontal scaling through sharding, which means the data is distributed across multiple machines. The scalability of MongoDB makes it more efficient when operating large amounts of data. Unlike MongoDB, pSQL is a relational database that supports both SQL and JSON. As same as other relational databases, pSQL stores data in tables made up of rows and columns. Users can define, manipulate, control, and query data through SQL. However, due to expansion, pSQL can not only support relational data, but also handle non-relational data now. It features transactions with asset properties, which we have learned in class. This helps the database maintain a high level of data integrity. Besides, pSQL supports automatically updatable views, triggers, foreign keys, and store procedures, so that people who seek for customization would be benefited from it. In addition, pSQL is designed to handle a range of workloads, from single machines to data warehouse with many concurrent users.
The import step in PostgreSQL requires a file in CSV format, and then its text content will be converted to a text search vector object, shortened to TS vector. Then it is ready for a future task. In comparison, MongoDB only takes JSON files, and it requires an additional indexing step. All indices of text content are stored in a B tree, and now it is ready to support text search. Both query planners are nested structures, but the one in MongoDB is more detailed. The queries to get the planner output are listed in this slide. We can see both queries contain the keyword explain, and the execution time section in PostgreSQL and execution stats section in MongoDB are used for later query performance comparisons. Doors will introduce you the planner output comparisons and the actual query output.
Next, we want to know how the execution plans differ from each other between the two techniques. In pSQL, the most common text search plan is sequential scanning. This means that all text tokens in TS vector will be traversed one by one. It is a very intuitive and straightforward plan, but not very efficient, since all word objects need to be scanned through using this plan. In MongoDB, the text search plan is usually text match combined with an index scan. As discussed in the course, indexing improves query performance by storing the data ordered by a specific field, so we expect to see less execution time in MongoDB's outputs. This leads us to the most important comparison in our study, which is comparing the execution speed. We do this by searching different words and phrases to see how long will it take for the two systems to execute the queries. pSQL shows the total query time in total cost section in the query planner, and MongoDB shows that in the execution time millisections. Here are some example queries. We try to search single word, single phrase. Two words appear simultaneously in a document, and one of the two words appear in the document. Here is the comparison table. pSQL takes about 20 to 30 milliseconds to browse through the whole document corpus. However, no matter how many times we test it, the execution time is always 0 for the MongoDB. This means MongoDB takes less than 1 millisecond to search the words, which is very fast.
There are some differences in the text preprocessing of the two DBMS. So first, introduce the difference in the stop words. In order to find out the difference, we try to conduct some experiments. For example, we search the keyword will and the single character s. And from the PostgreSQL, we will find that it returns no result for both searches. But for MongoDB, for both searches, it will say that there are 6 documents that could match the keyword. And in order to find out the specific difference in the stop words, we try to go back to the stop word list. And we find that for MongoDB, it will use the negation of the auxiliary verbs such as aren't, didn't, doesn't, and so forth. But for PostgreSQL, it will not use them. But for PostgreSQL, it will use some small stop words such as the will, the single character s, the single character t, and so forth. But this will not be used by MongoDB. There are also some differences in the stemming of the two DBMS. For PostgreSQL, it uses the Porter stemma. For MongoDB, it has its own rules. For PostgreSQL, the Porter stemma will replace the SSES with SS. For example, it will replace the stresses with stress. And also, you will delete the S if the preceding word contains a vowel not immediately before the S. For example, you will replace cats with cat, but it will not replace the word gas. And also, it will replace IED or IES with I if it's preceded by more than one letter. Otherwise, it will replace the IED or IES with IE. For example, it will replace ties with tie. And also, it will replace EED and EEDLY with EE if it's part of the word after the first non-vowel following a vowel. For example, it will replace agreed with agree, while feed will not be stemmed. And also, it will delete ed or edly or ing or ingly if the preceding word contains a vowel, and then if the word ends in like at or bl or iz, or if the word ends with a double letter that is not double L, double S, or double Z, the stemmer will remove the last letter. For example, the falling will be stemmed to fall. Or if the word is short, the stemmer will add the letter E. For example, the hoping will be stemmed to hope instead of hop. In terms of the stemming used by MongoDB, it depends on the search command. And we can see that for the search operator, the text search, it will have two fields. The first is called the case sensitive, and second one is called the diacritic sensitive. If the value of the case sensitive is false, the stemming will be case insensitive. And if the value of the diacritic sensitive is false, then the stemming will be diacritic insensitive. So we can find that for MongoDB, it has a less comprehensive stemmer, which will make it harder for the users to find exactly what they want. But for PostgreSQL, though its stemmer is much more complicated, it will lead to improper combinations of the words. For example, the word matrices, that is the matrics, and the word matrix, the matrix. These two words, the stemmer from the PostgreSQL will consider them as different. But obviously, these two words should be the same, and this is one type of the improper combinations of the words. In conclusion, the difference in the text search conducted by PostgreSQL and the MongoDB mainly happens in the efficiency and the results. In terms of the efficiency, the MongoDB outperformed the PostgreSQL by always using less than 1 millisecond to obtain the query result. So, the native support of MongoDB in text is definitely better than the extensive support in PostgreSQL. For the results, they differ due to the different stop words used by the two DBMS and also the stemming rules. Thanks for your watching.